Very good evening, all. Today we are going to see the video lecture series on Explainable AI. And in this video series, we are going to see about the topic called prototype-based explanation, that is called ProtoPnet. So this is one of the another important topic that we are going to see. Basically, the prototype based explanation is quite different than what we have discussed in the earlier lectures. That is, in the first lecture, we have discussed about glass box, black box, and after that, line, shape, cam, net to vector, how the information is processed by using vectors, and all these things we have discussed in the previous lecture series. But in here, we are going to see about the ProtoNet. That is totally a different concept, but it is a very easy to understandable theme that everyone can able to realize how easy the information is getting explainable. In that aspect, we are going into the lecture series one by one. And here you can see this is the actual blueprint of the thing what we are taking into account. This single diagram itself explain about the ProtoNet. That is what we are going to explain hereafter in this lecture series. Everything is tell in this single slide. You can see the word, this looks like that. This looks like that. That means, what is the meaning is, on seeing a single piece, we can able to realize this is going to be this. This is what we are going to speak about. Suppose we are seeing a tusk of the elephant, then we can, without seeing the entire image, we can tell that this is the elephant. We no need to scan the entire image of the elephant. Just we are showing a tusk itself. We can, for example, better I can draw here so that you can understand, right? So if I draw here like this, okay, some random diagram I am drawing. So please bear one if you are like this, and I am showing like this. That's it. Okay, so like this, I am showing. So example. So instead of either we can, the point of consistent may be either this portion or either this portion like this. So on the seeing these 2 points itself, we can able to tell, we can able to predict this is a elephant like that. On what basis we are predicting? Based on the two consistent patches. One is tusk and another one is the trunk of the elephant. So we can easily tell that with no other elephants are having the long trunk and tusks like elephant. So we can easily tell that this part or this patch is here part of the elephant. So in the same manner, you can see here we are projecting only one portion. This is called a patch of the image. So this consists of the feather colors and the wings, height of the wings and everything. So here we are going to calculate the distance between the two patches. So based on the closeness of the patches, we can able to identify this is confidently this belongs to a jay or a blue jay or a sparrow or a eagle. Like that we are going to predict whatever the images we are showing based on the patch information only. We are going to predict what is the actual image without scanning the entire pixels of the image. What is the advantage is confidential, the confident will be increased manner, as well as we can able to tell that due to this reason, I am come to the conclusion that this patches belongs to this animal or this bird or this disease like that. Okay. In the rest of the series, we are going to see how differently we can able to monitor or predict the patches of a certain criteria. This is called a ProtoNet. So So if you are building a big engine, for that we are having small prototype toy engine. But based on that, we can tell what we will tell. This is a railway engine. Okay, but that is not actual. That is just a prototype. So like that, based on the patches, small patches, we are going to tell that this is the image of a particular object or certain things. Okay, that we will see one by one hereafter. So the ProtoNet is a interpretable deep learning architecture designed to make image classification transparent and explainable. This is the main thing you have to understand. This is a interpretable architecture that make image classification transparent and explainable. Okay. So by means of comparing local regions with learned prototypes, already we are going to train with similar patches. Sparrow means these are all the things, different patches we are going to train. When you give a new input, the small patches only will be, that region of interest only will be taken into account. And depending on the closeness of the earlier learned objects or parts, we can come to the conclusion that how much close the results, that much confident is the score. So this is the theme of the prototype based explanation. Okay. So this is the saliency map. You can see here the post hoc saliency. We are posting some heat map over the sparrow image, but it is on seeing 2 or 3 times only we can came to understand that this is the image of the sparrow or a bird. Since it is looking around so many parameters, outside, inside, and close, only one portion is superimposed. So the model, where the model looks, but it is looking somewhere, okay, in the around the neck portion or the wing portion. We are showing only, actually the model is looking where, but we are not explaining about the logic why the model is looking in that portion, that we know. So the confirmation, sometimes the model may look perfectly, or sometime it may not. It may look in the surroundings that it may predict. So just like dog and husky. So the based on the snowfall, it is predicting it is husky, and non-snowfall, it is predicting it as a dog. Like that, the logic is totally non-transparent. That is, it is looking somewhere and it is predicting. So fails to provide legally accountable evidence. So on what basis you are telling? Only based on the particular region you are telling. Like that means there is no proper answer. But we are going for, in reality, we are going to form patches, and these patches are trained. So depending on the reality, so on the previously learned patches, we can came to conclusion that this is the image of the particular object. So this is the mimicking procedure. Mimicking procedure means we are creating the patches. Several data sets are trained, several patches are created. Based on the closeness of the patches, we will come to the conclusion that the particular space matches with the particular prototype. Okay, so this is the thing why this is called as prototype based explanation. So different patches are there. So on matching one patch with another patch, based on the closeness of the two patches, we can able to reason that due to this reason, this particular object belongs to particular criteria. Like, okay. So this is the detailed architecture of the ProtoNet. First, we are taking one chest image for reference, and here we are extracting the features, whatever may be. So 7 cross 7 cross 128 layers. So here what we are doing is each and everything is categorized into different prototypes. P02, P15, like that. So, and then what we are doing, the particular patch is mapped to a particular array. So this portion is map P0. That means either the topmost layer or the bottommost layer or the middle layer, everything is mapped to a particular that is called a consistent point, right? That consistent point where we are mapping that holds the P naught value. So different images we are giving means the topmost portion is once again mapped to P naught, middle portion is P1, depending on the training level, it differs. And then we are connecting it, everything we are connecting it to a fully learned weights. Based on that, after that, the same procedure, the weights will be adjusted and we will generate a logit normal and logit pneumonia, two cases. So based on the comparison of the prototypes, we can able to come to the conclusion that this image is the person is suffering from pneumonia or not, like that, based on the similarities. Okay. So here is the well explained diagram. You can see here. Now I am taking the thing called sparrow as explained here. And first we are calling it as backbone. That is the dimension is height, width, and this information HWD protocol. Okay. So it is converted into a arrays. The image is completely splitted into parts and it is converted into arrays. Okay, that is called latent feature map. Earlier I showed now this is called mapping. The same thing I am showing here, individual maps. After that, what we are doing, we are going to compare with P1, already learned image and already learned prototype with newly extracted prototype. This is equivalent to P1 or not. Already P1 is having certain patches. With that patch, this new patch is matching or not. Let's just like blood sample. We are comparing this sample is equivalent to this sample or not. Next sample, like that. Similarly, P2 is equivalent to this or not. PM is equivalent to this or not. Based on that, what we are doing, we are calculating the similarity scores. How similar? You can see here the first portion, we are seeing 3.954 and next portion is 1.447 and 2.64. This is computed by that algorithm, prototype algorithm. It will compute by itself based on the weights. And finally 3.578. So different images are having different weights and similarity scores. And finally, all are combined together in a linear head. That is weighted linear combination of the similarity scores. This is what I told earlier. Okay. So based on the linear weights, it outputs certain class logits. And based on the class logits, black-footed albatross, indigo bunting, cardinal, other combat. So which is having highest score, that will be the assumption. So 2.617 is the highest score. So that means the given image is definitely a cardinal based on this thing. So the patches is matching with that. So based on the patches, we are calculating the similarity score, which is the most highest similarity score. That result will be my output. So we can easily explain this to the aspirants that I came to the conclusion due to this. That's all. Here we are not telling where the model is looking. We are telling how the model is telling that this is. This is the important difference between um, the earlier traditional method and this prototype based explanation. This is what we are telling. Okay. So this usually first we are going to process the input into a Z dimension, three-dimensional feature, that is height, width, and diagonal. That mapping HWD format. Okay, that I will tell you in afterwards. So this is latent similarity is directly inversely proportional to the L2 distance. Okay, so we are going to find the similarity between two cases and how close, how inversely proportional, right? So how smaller the distance, that will be the expected score. So calculate the L square distance between jth prototype and the spatial patches, already trained patches with the input. Inverts the mathematical distance into similarity scores. Well, so by taking the inverse, we can able to convert that mathematical distances into similarity scores. Then we are generating a heat map, and then the presence of prototype we are going to estimate. This is the logic behind how the prototype net is, or this is the formula between how we are estimating the similarity score. This is the formula. Okay, so this probability, that is P of J, is the probability, that is the distance, and the mapping ZAP is the mapping of two patches. Already I told what are all the how the prototypes are patched. So here we are taking only A and B. So A and B, how it is closely related to each other, that we are calculating here. So this is the three stage. First, what we are doing, join the SGD. Okay, so phase one is just this is the backbone stage, that is CNN stage. So this cross entropy plus cluster loss plus separation cost. So these are the joined pattern. And phase two, what we are doing, we are prototype projection. We are projecting the proto. First, we are getting the images, and we are converting into prototypes into small projections, and we are focusing. And finally, the weight matrix is adjusted, and based on the positive weights, and positive weights will gain the rewards, and negatives will get penalized, that is filtered. So based on the positive weights and high scores, we can able to predict whether this model belongs to this particular category. So this is the, once again, this is the detailed explanation what we have done. So this is same sparrow image. You can see a particular patch that is converted into layer, and it is split into different prototypes. And what is the maximum pool? That is the distance score, everything. So again, we are same diagram only, but we have converted this into a well-defined thing. Same explanation. Previously, what we did, same thing only here we are doing. Okay. So here, this is the step-by-step architecture. First is we are going for the feature extraction. That can be done either by ResNet or VGG. So input image and output features is splitted it based on the height, width, and dimension. We are just splitting the input image into different layers, and based on the layers, we are going for prototyping. So that is mapping to the array. That is the second stage. And third stage is based on the fully connected layer maps. We are estimating the similarity scores for doing the class predictions. So final output will be in the logits. That is logical bits. It may be. Okay. So let us take this example, classification of a bird image into either sparrow or eagle. So input image I am taking for your understanding, we are considering this function as a 4x4 function. So what is the next stage is prototype 1 sparrow, that is small beak. So I am giving the weightage as 1,2, and sparrow short wings, that is 5,1. Eagle large curved beak 4,5. Okay, and small means 1, like that. Short wings, like that. It is classifying. How it is classifying, that depends on weightage and training, that we are unable, we cannot explain in a manual mode. By studying the algorithm and training weights only, we can be able to assume the weight on a particular pattern. So similarly, broad wings, it is having highest weight 8,1. This is the thing what we are estimating in a two-dimensional fashion, but algorithm will work in three-dimensional mode. That is height into width into D. We are telling that. But here we are showing, for simplicity, we are showing height and width only. Okay. So we are computing using this formula, norm of minus. How it is calculating? Let us check. 4,4 minus 1,2. First, 4,4 is the standard. This is the input image. These are the learned patches. Okay, so according to prototype 1, 4,4 is compared. So minus 1,2, we get minus 13. Similarly, 4 comma 4 minus 5 comma 1. You can see here next short wings. So we are getting the value as minus 10. Similarly, 4 comma 4 minus 4 comma 5 minus 1 and 8 comma 1 minus 25. This is how the similarity computation on how close the similarity is inversely proportional. That is what I am telling. Minus 1 will not be the final score. This is too close, so it is not the result. Which is too far, that will be the, due to inversion, it will be converted into the scores. Okay. So this is how the see here, the beak is matched the prototype of 14th prototype. We are training for a beak classification. So it is matching with this. And similarly, prototype 14 matches with the wings also. And similarly, prototype 14 is matched with the this portion also. So the similarity scores will be looking like this: class weight into 1.180, similarity score is 6.449. So based on that, we come to the conclusion that 7.669 points we are getting. So how it is predicting, we are based on the prototype 14, we are mapping these things. So prototype 14 is nothing but the given input image is matching with all these properties. This beak size, wing size, tail size, color, everything it is matching. And based on the similarity score, which is the highest score, we can able to identify that this is the this object will be like this. Okay. So this is another diagram, physical reality. So actual latent patch, we are not seeing the entire thing. One consistent portion only we are checking. So every provided during the interference is tangible visual pieces of historical evidence, not a hallucination. So it is not a wrong. It may be like that, not in a particular portion. Due to this impact, I am telling that this is the bed. That is what is the thing. So every 10 epochs, only after 10 training, the abstract latent prototype vector with the nearest actual latent patch will be taken into consideration. Training set sharing the same label. So every 10 epochs, this will be matched with the input image, and it will check whether we are getting the same scores or not. Every 10 scores. If it is not getting, means that will be we cannot be able to proceed further. So every 10 times we have to check the near actual latent patch is matching with the training set or not, approximately. If it is okay, it is getting closer, means we can continue. Otherwise, we cannot continue with the applied image. We will go for next patches to compare. So only one image we are comparing for 100 or 1000 time, means it is waste of time. In the 10th patch itself, result is not coming. Accuracy is very less, means it is not possible to concentrate in that particular image once again. So we will go for another set of patches with another 10 epochs. So whichever similarity score we are getting, based on the training will be increased. Okay. So here, this is the nonlinear evidence order and two things. So prototype, you can see here, similarity is 8.91. Okay, so replaces the flat linear head with a soft, just on decision tree, we are eliminating. So exact visual prototype triggered a false positive, enabling immediate targeted retraining. So based on that, what we are doing, if it is not the expected, means it will again uh, enable the immediate targeted retraining. Once again, it is trained with different patch. That is the thing. So here also you can see rigid